Okay, the next topic is the adjacency list. Well, just now we talked about the adjacency matrix, and the problem is, well, if we have a very sparse graph, and then in the adjacency matrix, and we know there are going to be really a lot of the zeros. And however, and remember, well, this takes the OV square. So OV square is the required memory space to store a adjacency matrix, and this can be too much for a sparse graph, and especially for a sparse graph which has really a lot of the vertices. So the next choice we have is adjacency list. So in this case, well, we are using the same graph, and we have a total of 4 nodes. In this case, for each of the node, we want to record what are the edges available from this node to other nodes. So for example, the adjacency list with the index 1, that is how many edges are going out from the node 1. And then in this case, well, from the node 1 we can go to node 2 and node 3, and for node 2 we can go to node 3, and for node 3 we can go nowhere, and then for node 4 we can go to node 3. Okay, so this is the idea of storing the graph with a adjacency list, and you may feel like this may work better if we have a very sparse graph. Okay, and the variation is, well, if you want to keep the list of the edges coming into the current vertices, and that it can also work that way. So for example, adjacency list with the index as 3, that is empty because there's no edges going out from the node 3, right? So if you want to use this kind of variation, and then instead of storing what are the edges, what are the nodes that we can go out to, we can record what are the nodes that we have incoming edges. In this case, well, the adjacency list with the index 1, that will be empty because there's no nodes going to 1. And then for 2, and we will have a 1 there because, well, from 1 we can go to 2 because in this variation we are recording not outgoing edges but incoming edges. Okay, and then for the 3 we will have 2, 1, and 4 because from 2, 1, and 4 we have incoming edges to the node 3. So this is a possible variation, but we don't use that a lot. Okay, and the next topic we want to say is the degree. So the degree of a vertex is the number of the edges. So we are counting the number of the edges. Well, it depends on if you're doing a directed graph or a undirected graph. So if you're doing a directed graph, and then we have to count the in degree and the out degree. However, if you're doing a undirected graph, and we don't need to bother to count to differentiate the in degree or the out degree, and we simply say the degree of a vertex V. So let me go to example here. So if you're using a directed graph, so if you're picking the 2, for example, so for the out degree of the 2, so out degree of the 2, that is how many outgoing edges. So the out degree 2 of the 2 is a 1, and the in degree 2 is a 0. Okay, and how about 4? So for the 4, there are 3 incoming edges. So for the in degree of the 4, that is a 3, and for the out degree, that is a 0, right? So let's come back to this point. So for a directed graph, the number of the items, the number of the adjacency list is the total number of the out degree, which is E. So why? So in this case, how many edges are we recording? We are recording only 1, 2, 3, right? We are only recording 3 edges in this case. So that is for the adjacent 1, we will have a 4. And then for the ADJ2, we have a 4. For the ADJ3, we have a 4. And then for the ADJ4, we have nothing. Okay, so in this case, we are creating a total of 4 slots because we have 4 nodes or 4 vertices. And then we are only recording 3 values because there are only a total of 3 edges in this case. So the number of the edges and then the number of the vertices, and that is all we need to store a directed graph, right? So in this case, we are recording, say, we are creating a total of 4 slots, and then on those 4 slots, we are only storing a total of 3 values because 4 is the number of the nodes and the 3 is the number of the edges. Okay, so let's see another one. So how about the undirected graph? So for the undirected graph, and we will have the ADJ1 as a 4, and the ADJ2 is a 4 as well because 1 is connected to 4, 2 is connected to 4. And then for the ADJ3, it's a 4 again. But how about the ADJ4? For the ADJ4, 4 is connected to 2, 1, and 3. And because that is an undirected graph, and then it will be a list of 1, 2, and 3 in this case, right? So this is an undirected graph. So how many nodes are we storing? We are storing 4. So for the adjacent list, there are a total of 4 slots again. And then how many values are we storing in total? And then we are counting 6, right? Because for each of the edge, if we can go from 1 to 4, so from 1 to 4, and then from 4 we can also go to 1. So for each of the edge, we are going to count that twice. So that is the reason that we have a total of 6 edges counted here. But anyhow, the sigma, the total number of the edges should be the 2e because we are doing handshakings, okay? But that is still a sigma of the v plus e storage. So putting this information together, it doesn't matter if we are storing a directed graph or undirected graph. The memory cost of storing a adjacency list should be O V plus E. Okay? So the next task we want to talk about is to do a graph searching. Well, and for this search, and we have multiple goals, and well, we can accomplish all of them together. So we are given a graph that is a G, and that is a collection of the vertices and plus a collection of the edges. And well, it doesn't matter is it directed or undirected, okay? And our goal is we want to explore all the vertices and all the edges, and ultimately we also want to build a tree based on this graph. So we pick a vertex as a root, and then we want to change the certain edges, well, to produce a tree. So well, for the entire graph, we are only picking part of the edges to build a tree structure. And in some of the cases, if not all the vertices are connected, and then it is not really possible to build one single tree, and in this case, we may have to build a forest. So when we are trying the strategy of exploring a graph and turning that into a tree, and the strategy will be, well, we only visit one vertex at one time, And then based on the current vertex we are visiting, and then we are trying to expand the frontier of the explored vertices, and then across the breadth of the frontier. Okay, so we are doing a breadth first search. So we are expanding the frontier of the explored area across the breadth of the frontier. Okay, so build a tree over a graph. So we have to pick a source vertex, and that will be the root. So we are specifying which root we are going to take as the root. So when we are doing the breadth first search, and the strategy is we want to again associate each of the vertex with a color. So the definition of this algorithm is if we are coloring a vertex to be white, and then it is just an unvisited node yet. Okay, so and to start this algorithm, and all the vertices are white, are colored to be white. And then for the gray vertices, and they are discovered vertices, but yet they are not fully explored yet. And then after we have fully explored a vertex, and then we will color that into black. Okay, so well, we are gonna continue the code in the next video.